In this task, we're going to calculate the ionization energy of the group 2 alkaline earth element magnesium. So we'll start by opening the WebMO app, and on the opening screen we're going to select a magnesium atom. So we use the menu at the top, we select P table, the periodic table, then from the second group on the left hand side we select Mg for magnesium, and then tap anywhere on the screen to generate our magnesium atom. So this is the atom that we're going to perform our calculations on, and the way we're going to calculate the ionization energy is we're going to take the difference between the total energy of the neutral atom and of the cation. And this is going to represent the energy required to change an atom into its cation, to liberate an electron, to ionize the atom. Now we define an ionization energy as having a positive value, i.e. it's the amount of energy that we need to contribute to the system to cause the ionization process. And so the way we want to evaluate this is to evaluate the total energy of the cation and subtract the total energy of the neutral atom. And that's because the neutral atom is more stable than the cation, and so subtracting the total energy of the atom from the cation will give us a positive value. So the first thing we want to do is set up the calculation for the evaluation of the total energy of the cation. So we select WebMO from the menu at the bottom, and then Submit from the menu at the top. So we're firstly going to change the job name. The job name is defaulted to Mg, but of course we're going to be calculating Mg plus the cation. So we just tap in that box and we just change Mg to Mg plus. We can leave the calculation as it is. We want to evaluate the molecular energy. We're going to change the theory again from Hartree-Fock to B3 lip. Remember, the theory is the approximation we use for the electron-electron interactions. And we're again going to change the basis set to CCPV-TZ, this large basis set, to ensure we can describe the motion of the electrons accurately. Now, because this is a cation, we also have to change the charge of the system. The charge is currently 0, which it would be for a neutral system. We need to delete that and change the charge to 1, so +1 for our cation. And this changes something about the electronic structure, and we're not going to get into the details of what that change is, but it means we need to change the multiplicity from singlet to doublet. It reflects the fact that in the cationic system, we don't have a closed shell electronic structure anymore. Each of our atomic orbitals is no longer doubly occupied. So that's the calculation set up. So we just tap on the blue button on the bottom right hand side of the grey panel, and that submits our job. We see the job is running. It'll just take a few seconds to complete, and then we can evaluate the total energy. So the job's completed. It took 4.5 seconds, and now we simply tap on the name of the job, Mg+, and that opens up the results from the calculation. We tap on results, and we're interested in this energy here, minus 199.813693718 Hartrees. So this is the total energy of our cation, and we need to record that somewhere because we need to compare it to the total energy of our neutral system. So if you just tap the blue arrow in the top left of the screen, that will take us back to our results page, and we can actually then straight away perform the equivalent calculation on our neutral atom. So we again tap Submit. It defaults again to Mg for the job name, but actually that's what we want in this case. We want to calculate now the total energy of the magnesium atom. We again want the molecular energy as the calculation. It's very important we select the theory to be the same as the theory we use for the cation. If we use a different theory here to the theory we use for the calculation of the cation, our results won't mean anything. So again, we select B3 lip, and again, it's important we select the same basis set, CCPV-TZ. Now we are calculating a neutral atom here, the magnesium atom, and we can describe the multiplicity as we've usually been doing as a singlet. So we don't need to change anything else here. We just tap the blue arrow in the bottom right hand corner of the panel and let the job run. This is a very similar calculation to the last one we did, so we'd expect the calculation to just take a few seconds as it did for the cation. And there we go, it's slightly faster, and that reflects the fact actually that we're dealing with a closed shell system here, which are a little more efficient to evaluate. But we do the same thing, we now just tap on the name, MG, the job loads, we tap on results in the menu at the top left, and we just record this total energy here, minus 200.097698,406. And you can see that energy is lower because it's a negative value. It's a lower energy than the energy we evaluated for the cation, and that ensures when we subtract this energy from the cationic energy, we'll get a positive value, and that positive value will be our ionisation energy in atomic units.